Hi, welcome to yet another MDE paper of the week. We're trying to catch the backlog of papers we haven't read, so there's going to be quite a few presentations coming out all in one go. So the paper for today is Seehusen and Stølen. Not very good at pronouncing Scandinavian names. An evaluation of the graphical modeling framework (GMF) based on the development of the coras tool. Now it switches gears a lot from the previous paper that we read, because where in the previous paper we were talking about things that preceded MDE and sort of MDA and that sort of thing. Here we are in the guts of it really. These GMF and EMF and Eclipse are really the technologies that came out of MDE. So this is really very, very different from the previous paper. The main reason why I'm interested in this paper is just to make sure that we really got a good understanding of what EMF offers, because since we decided not to use it, we need to make sure we can explain why and what are the differences in approach. So we're very, very keen to understand this a bit better. So let's have a look. We present an evaluation of the graphical modeling framework, GMF, based on our experiences in developing an editor for the risk modeling language coras using GMF. Our main hypothesis is that GMF shortens the development time and results in more reliable and maintainable systems than alternative approaches which are not based on code generation. Okay, very strong hypothesis there. We conclude that the hypothesis is true, but the answer is not as clear-cut as we initially believed, and that there is still a large potential for improvement. Okay. Presumably this is the teachable moment, I guess, of this paper with difficulties. So, introduction. We present an evaluation of the graphical modeling framework GMF based on the experiences we got from developing a graphical editor for the risk modeling language coras. This is really nothing to do with the stuff we're doing, but it's worthwhile keeping an eye on this coras. Let's just make sure we highlight. This may have other applications outside of just modeling. So we'll leave it a marker here just so we remember. GMF builds on the principles of model-driven development, MDD, slightly before MDE, which advocates that you use design time models as the basis for code generation. Not quite right, but in the area of domain-specific languages, the idea of generating code from specification is not new. So-called parser generators have been in use for a long time. These tools usually take an EBNF grammar as input and produce parsers that transform concrete syntax, such as source code, into abstract syntax. So basically, this is just grammarware. The idea of GMF is similar, the main difference being that the grammar is specified. The main difference being that the language grammar is specified as an equal model, similar to YAML class diagram model, instead of EBNF. That concrete syntax is graphical, not text-based as in the traditional case, and that GMF not only generates a parser but also much of the language editor. So this is basically the general idea with GME. You can generate a complete editor. When you create a language, you get everything with it. You get the IDE, you get everything with it. The language that we developed an editor for is called the coras language. The language is graphical and is used for the purpose of documenting a risk analysis. The coras language editor was developed as a part of a book release on the coras risk analysis methods. Software development in the industry is usually not based on code generation from models. We are therefore primarily interested in comparing the use of GMF to development approach which is not based on code generation. Okay. Our main hypothesis is that GMF shortens the development time and results in more reliable maintainable systems than alternative approaches which are not based on code generation. Our evaluation suggests that GMF does shorten development time, but is similar to a smaller degree than we initially expected, as we already highlighted. The main reason for this is that the code which is generated by GMF had to be modified, and this turned out to be very time-consuming. Our evaluation furthermore suggests that GMF may result in more reliable systems, but that it does not result in more maintainable systems. Right, this is all extremely interesting, particularly the maintainability side of it. The main lesson learned during the development of the coras tool was that there is a huge difference in practice between transformations that produce code that to little or no degree should be modified, like parser generators or compilers, and transformation codes that produce code that must be modified. In the former case, it is reasonable to hide the details of the transformation from the developer through configuration options, but in the latter case, this is more problematic. Okay, this is very, very, very important. In fact, we believe that in the latter case, the transformation should not only be visible to the developer, but that the developer should be expected and accommodated to modify the transformation, much in the same way that the developer is expected to modify the generated source code. We are highlighting pretty much everything here, but the rest of the paper is structured as follows. In section 2, we introduce basic concepts of GMF. In section 3, we describe our research method and hypothesis. In section 4, we describe the relevant facts about the coras tool and its development process. In section 5 and section 6, we evaluate GMF with regards to hypotheses and suggest improvements, respectively. Finally, in section 7, we present related work, and in section 8, we provide conclusions. Interesting that related work is 7 rather than 3 or sort of early on. So let's have a look then at the GMF. So the GMF is divided into 3 layers, very familiar architecture. The meta model at level 0, configuration at level 1, a generator model at level 2, and the source code at level 3. So the meta model is eCore, as expected. eCore then goes into gen model, which is model for the generation, and then from there we go to the EMF code generator. eCore models for configuration as GMF map, probably this is a feature model of some kind, GMF tool, and GMF graph, so presumably these are just to manage configurations of features and so forth. This produces a generation model for features, those two get bound together, and that's where out comes the code. GMF is a framework for developing domain-specific languages. GMF is built on the Eclipse modeling framework and the graphical editing framework, GEF. In the context of GMF, EMF is used to define the meta model, or abstract syntax of languages expressed in eCore, and for generating code for creating, editing, and accessing models. GEF is a framework that supports the development of graphical editors. In the context of GMF, GEF is used to implement the concrete graphical syntax of languages and for editing concrete syntax. Transformations of GMF are illustrated in figure 1. The topmost transformation consisting of the 2 arrows taking eCore into EMF code, which will be referred to as the EMF transformation, while the arrows taking eCore into GMF code will be referred to as the EMF transformation. So this is the EMF transformation, and this is the GMF transformation, presumably. Probably should highlight this bit here. As illustrated in figure 1, we distinguish between 4 different levels, so this is what we were talking about a second ago. The meta model level 0. This level contains the meta model, which is the basis of code generation. The meta model used by GMF must be stored in the format called eCore. The configuration level 1. This level contains the configuration model, which is used by the GMF transformation. This is not used by the EMF transformation. The configuration model consists of 3 files. One file which is used to specify the shapes of the graphical constructs of the language, GMF graph, and one file which specifies the language constructs which should appear in the tool palette of the language editor, and one GMF tool, and one file GMF map, which maps items of the tool palette defined GMF tool to the graphical language constructs defined in GMF graph, and to the meta model elements. So really, when I was thinking about feature models, but really this is just basically the configuration of the language itself, really. The default transformation from the meta model at level 0 to the configuration model at level 1 is based on a series of dialog windows where the user has to specify what elements of the meta model should be represented as arrows or nodes in the language editor. The generator level 2. This level contains the code generator models for both EMF and the GMF transformations. Both generator models contain a number of parameters that allow the user to customize the source code generated from the generator models. Transformation from level 1 to level 2, or from level 0 to level 2, in the case of the EMF transformation, is one button transformation as opposed to dialog-based transformation. Source code level 3. This level contains the source code. Here we distinguish between the EMF code generated by the EMF transformation, GMF code generated by the GMF transformation, which makes use of the EMF code as well as the GEF framework, the modified GMF code, i.e. the generated GMF code which has been modified after generation, and custom code which has not been generated from the meta model but which makes use of the EMF code and the GMF code. Note that we do not distinguish between generated EMF code and modified EMF code. The reason is that we did not have to modify the generated EMF code, even though this is possible to do so. Transformation from level 2 to level 3 is also one button transformation. However, the GMF framework, the GMF transformation from level 2 to level 3, which is written in a language called Expand, this is the templating language, can be customized. This was achieved by putting the files containing the transformation specification in a special folder with the same structure as the GMF transformation. When the transformation is executed, the transformation in the special folder will be used instead of the original transformation. The effect is essentially the same as modifying the original transformation directly. In theory, although the modified GMF code could have been specified in the transformation from level 2 to level 3, the GMF is not intended to be used in this way. Instead, GMF code, which is modified after code generation, can be tagged to ensure that modified code is not overwritten when the code generator is executed at some later point in time. This is interesting. Let's put a note here. Investigate how GMF code that is modified after code generation is tagged so that the generator knows not to overwrite it. This would be something we could probably reuse. So, on to the research method and hypothesis. According to 12, research evidence is gathered to maximize three things: the generalizability of the evidence over populations of actors, the precision of measurement of the behavior, the realism of the situational context. Okay. According to the classification of research strategies of 12, our evaluation of GMF is a field study. Field studies are high on realism but low on generalizability and precision. Important this. The idea of evaluating GMF did not come about until after we had developed the coras tool. Therefore, the development of the coras tool was not in any way biased by our evaluation. We are primarily interested in comparing the use of GMF to a development approach which is not based in code generation. For us, a realistic alternative to using GMF would be to use Eclipse and GEF. The main differences between the GMF approach and the alternative approach is that using the alternative approach we would have had to write code that uses GEF instead of generating it using GMF, and write the code with similar functionality as the EMF code instead of generating it using the EMF transformation. Throughout the rest of this paper, whenever we write whenever we write the alternative development approach or alternative approach, we refer to the approach described above. Note that we did not actually develop the coras tool using the alternative approach. So this is basically the judgment call. And any judgment about the coras tool, for instance, how long we have taken to develop the coras tool, had we used the alternative approach, is therefore based on educated guesses rather than facts. Hypothesis. The main reason why we chose GMF was that we believed it would shorten the development time. In fact, one of our colleagues claimed it would only take 2 days to develop the editor using GMF. Another colleague estimated that it would take about 2 weeks. Granted, our colleagues were not familiar with the requirements of the tool, but were nevertheless given to believe that using GMF would shorten development time. Our first hypothesis, therefore, the time spent on developing the coras tool using GMF is shorter than the time spent on developing the tool that we follow the alternative approach. The coras tool was intended to be used. So before we do that, we probably should highlight this. The coras tool was intended to be used on industrial settings, often often on the fly during customer meetings. Consequently, the most important requirement of the coras tool, aside from the fact that it had to support desired functionality, was the continuous delivery of correct service, and also known as reliability. Our second hypothesis is therefore the coras tool is more reliable when developing using GMF than it would have been if developed using the alternative approach. From the start, it was anticipated that the coras tool will be extended into new prototype tools according to the requirements of projects we were involved in. Already, we have made 3 such extensions, and further extensions are planned in the future. The situation can be described by an inheritance tree where the initial coras tool is the root of the tree, and each of the other 3 nodes represent extensions that inherit functionality from the parent nodes in the tree. Quite interesting. We are interested in evaluating how well GMF supports the maintainability of such an inheritance tree. Very interesting approach. For the purposes of our evaluation, we therefore say that the maintainability of a tool is a measure of how well it can be extended into an inheritance tree that satisfies the following requirements. The development of a tool in the tree should not affect any of the parents of that tool. This requirement is to make sure that development of new tools does not cause the tools they inherit from to become unreliable. Updates made in a tool should automatically or semi-automatically be propagated to all of its children in the inheritance tree. Excuse me. If we did not have this requirement and made a change in the root node, for instance, we would have had to manually update all the other tools of the tree. This would be time consuming and could potentially lead to reduced reliability. So our third hypothesis is the following. The coras tool is more maintainable when developed using GMF than it would have been if developed using the alternative approach. So, developing the coras tool using GMF. In this section we present facts regarding the coras tool and the development setting. So there's a screenshot of the coras tool. Difficult to see. See if we can make the screen slightly bigger. Right, so a lot of domain-specific things, threat scenarios, human threat. Okay, so this is all quite domain-specific to risk analysis. Let's get our Emacs back to where it was. This development setting. Initial discussions about the coras tool started in December 2009. The requirements were complete in September 2009. The tool requirements were complete in December 2009. The tool development was carried out by a single developer from the end of December 2009 until early May 2010. From February 2010 to May 2010, the developer was close to full-time on the coras tool developments. The total time spent in development was around 3.5 man-months. The developer is employed as a researcher and has a computer science background. His programming experience was mostly based on university graduate courses. The developer was somewhat familiar with Eclipse, the integrated development environment that supports GMF, but had no experience with GMF or the component that GMF builds on, EMF and Jeff. The developer was under pressure to finish coras tool as quickly as possible. The development approach was based on trial and error, thereby learning exactly what was needed to get the job done. We do not argue this is the best development approach, but merely give an account of what's happened. Moreover, we believe that this situation is not uncommon in many industrial projects, software projects. The coras tool. Coras tool is a graphical editor for the coras language, which is used for the purpose of documenting risk analysis. Coras diagrams are essentially graphs with arrows and nodes. The coras tool supports 5 kinds of diagrams and also supports a hierarchical structure in which one construct may be decomposed into other constructs to an arbitrary depth. A screenshot of the tool is shown on figure 2. Table 1 summarizes some statistics about the coras tool implementation. Here, the number of modified generated code lines is estimated to be 10% of the code lines of the classes that had to be modified. All the other values are accurate facts, not estimations. We have distinguished between code which has been generated by EMF code generator and code which has been generated by the GMF code generator. Notice that this is only the generated GMF code that had to be modified. Notice also that 18.5% of the generated code, generated GMF classes had to be modified, and that about 0.6% of the code lines had to be modified. So I just, I mean, this is always a little bit, you have to take this with a grain of salt because it's very difficult to make too much out of percentages and lines of code and that sort of thing. So it's good to have numbers in the papers, but let's proceed. Evaluation of GMF. In this section, we evaluate GMF with regards to each of the hypotheses described in section 1. The time spent on, so hypothesis 1, we know what this is. So the development of the coras tool took about 3.5 man-months, which was more than we anticipated. Since we did not have a stable meta model to begin with, it actually only took a couple of days to generate an initial version of the editor containing most of the required functionality. The problem was the huge amount of time required to modify the code that was generated. So this is a classic problem with code generation. It's probably worth highlighting this in red. So you first get something out very quickly, but then spend a lot of time trying to get it to the shape that you need. Not much of the generated code had to be changed. See table 1, but finding the right places in the generated code to implement the modification was very time consuming. It was not uncommon to spend days to search for the right place to edit, only to change a couple of lines here and there. Another very common situation. So why did it take so long? Highlight all the problems in red, I guess. One reason is that the developer had no prior experience with GMF or the technology used by GMF, GEF and EMF, and as it turned out, too little knowledge of Eclipse. Any of these technologies are challenging to learn on their own right. Learning them all at the same time is even more challenging. Another aspect is poor documentation. In particular, the source code and the API contain very little documentation. Despite the fact that I had a book on GMF, this book did not address the very specific challenges that we had to make to generate the code. Changes that we had to make. Most of the answers we got were found by browsing the source code, as well as in blogs, forums, presentations, small tutorials found by searching the net. A lot of the changes we made to source code that was generated from GMF had to be applied to numerous classes. That is, the same change had to be made to many classes of the same kind, usually meaning that they inherited from the same superclass contained in a library. Eventually, the developer learned to modify GMF transformations that generated the code, the source code, to implement these kinds of changes. Very interesting as well. Of course, I wonder what causes these changes not to kick in. Of course, if the developer had been aware of these things from the start, much time could have been saved. This is also true from the GMF transformation, from the meta model to the generator model. Eventually, he found an alternative to the GMF transformation wizard called Eugenia, which is built on top of Epsilon, which allowed us to generate the graphical configuration files from an annotated meta model. This worked very well. It was very easy to learn, and the execution of the transformation was reduced to pressing a button as opposed to clicking through a series of dialogues. Up until this point, we've argued that most of the development time was spent on modifying generated code. However, to address this hypothesis, we must ask whether GMF shortens development time. To answer this question, it is useful to distinguish between the EMF transformation and GMF transformations as explained in section 2. The former transformation generated code, which we did not have to modify. The former transformation generated code which we did not have to modify. This is the problem of reading papers late at night, I'm afraid. In our view, the use of the EMF transformation clearly saved us a lot of time. It should come as no surprise, since the EMF transformation is similar to well-known parser generators, which are clearly useful. Okay, maybe a bit of green here, I guess. Oh, so used to pink. The GMF transformation is more complex than the EMF transformation. First of all, it has a lot more configuration options, e.g. for customizing graphical constructs that should be implemented. Our initial goal was to do as much of the customization as possible on the meta model level and on the configuration level. So quite some time was spent on figuring out whether or not it was possible to specify the kind of graphical construct that we needed using the configuration files instead of having to modify the source code. It turned out that it was not possible, and eventually the configuration files were mostly ignored in favor of source code modification. The main difference between the GMF transformation and the DMF transformation from the perspective of time use was that the code was produced by GMF transformation had to be modified, whereas this was not the case on DMF. As already explained, the code modifications turned out to be the biggest time drain. Since figuring out how to modify the code to such a long time, it is hard to say for sure whether or not it would have been faster to write all the generated code from scratch. However, if we were to make a new graphical editor with the knowledge we have today of how GMF works, we definitely think that using the GMF transformation will be faster than writing the code from scratch. So this is always the key. You need to go through the pain first. We therefore believe that the hypothesis H1 is true, but the answer is not as clear-cut as we believed to be when we started developing the tool. H2. As we mentioned in the previous section, GMF had some bugs, but these were more the kind that slowed us down rather than making the generated code unreliable. After having tested the coras tool on students, we have found that any serious error in the GMF code, apart from the copy and paste, we have not found any serious error in the GMF code, apart from copy and paste functionality. The few errors that were found were caused by us rather than GMF code. That's good. The generated GMF code seems to be based a lot on standard design patterns. This is probably mostly an advantage, but not necessarily if the developer who has to modify the generated code is not familiar with those patterns. Had the developer written the code from scratch, he would have used patterns that he was familiar with and could understand, would have therefore have a much better understanding of how the code works. Furthermore, the code base would have likely been smaller and more manageable. Quite an important point here. Turn to our red. In general, we can say this: the time and effort spent on verifying the GMF transformation and the code produced by it is probably greater than the time and effort we could have spent on verifying the code we would have written had we followed an alternative approach. In this sense, the generated code is potentially more reliable. However, if the generated code must be modified, then the picture is less clear. The reason for this is that modifying the code that's unfamiliar to the developer, and which furthermore may be based on patterns that the developer is not familiar with, may cause the developer to modify the code in a way which is not intended to be modified. However, if we follow the alternative approach, we will still have to use the GEF, which is based on certain design patterns that must be followed in order to use the framework properly. In fact, it is probably less likely that GEF is used incorrectly in the generated code than it is that the GEF had been used incorrectly as we follow the alternative approach. Makes sense? As explained in section 2, the first time the GMF transformations are executed, output is generated which has to be modified. When the transformations are executed again, they will override parts of the output which was generated from the previous execution and leave other parts unchanged, presumably modified parts. Regarding the transformation from the meta model to the configuration level, and from the configuration level to the generator model, it was a bit unclear to us which parts would have been overwritten and what parts would be changed. Okay, this is very interesting. Quite annoying. The reason for this is that the developer had to explicitly annotate methods in the generated code to indicate that they should not be overwritten during the next execution of the transformation. Okay. However, the approach does not... Okay, let's just mark this down. Green, perhaps? Let's go for green and... get some green here. Green and red. However, this approach does by no means guarantee that the transformation does not generate errors in the code next time it is run. That is, changes made to the meta model or on the configuration model could result in a modification in methods that have been specified not to be overwritten. The considerations above are potential sources of errors, but did not, as far as we know, turn out to be any problem with regards to the reliability of the coras tool. However, it is difficult to determine whether this was a coincidence or not. Excuse me. In conclusion, we believe that the hypothesis is true. This is all quite difficult to measure, really. The main reason for this is that we did not discover many errors which affected the reliability of the GMF code. Most of the errors we found were caused by us. Okay. Source code which is generated and should be used many times is more likely to be subject to a more detailed verification process than code which is written from scratch. Despite, okay, this is clearly a very important point. Shame we have to change page a few times, but there we go. Despite the danger of modifying the generated code in a way that violates the design patterns that are used, this danger also exists in the code had been written if the code had been written from scratch using third-party libraries such as GF. The possibility of modifying the output of a transformation may potentially lead to errors when transformations have to be executed several times. However, according to our experience, this did not affect reliability of the coras tool to a noticeable extent. So, the coras tool is in H3. As explained in section 3, the coras tool had been extended into 3 new tool versions. In the process of figuring out how to maintain those different versions, we discovered that code generation actually made things a lot more difficult for us. Perhaps a bit of red. We will now explain this. Consider a scenario in which we want to extend tool A into a tool B. By this we mean that we want to develop a new tool B that has a lot of the same functionality as A, but some of the functionality a bit different. A standard solution to the problem is the following. Package A into a component, e.g. a Java jar file or an Eclipse plugin, that can be used by B, e.g. by invoking methods exposed by the public interface of the component or subclassing public classes of A. The problem, however, is that this standard solution is not supported in GMF code generation setting. To see this, consider figure 3. Here, tool A has been decomposed into 2 parts, model A and code A, where the idea is that code A is generated from model A, the same applies for tool B. To extend A into B, it is possible to both extend the model and the code. Imagine that we try to apply the standard solution to the problem. We get the following scenario. First we package the source code of A into a component, then we make a folder project for B, and then import component A into it. Suppose that the model has to be extended. Since it is not possible to package the model into a component like source code, model A is copied into folder of B. The problem now is that when code B is generated from model B, code B will contain much the same functionality as contained in package A, and will therefore be very inconvenient to try to replace the functionality code B that overlaps with package A, with invocations of A. This is actually quite an important point here, but I'm not quite understanding. Let's just try to read this again. To extend A into B, it is possible to both extend the model and the code. Imagine that we try to apply the standard solution to the problem. We get to the following scenario. First we package the source code of A into a component, then we make a folder project for B and import component A into it. Suppose that the model has to be extended. Since it is not possible to package the model into a component like source code, why not? Model B is copied into the folder of B. The problem is now, when source code is generated from model B, code B will contain much of the same functionality as generated in package A, and will be therefore very inconvenient. So I don't fully understand why this is the case, because this is exactly what we intend to do with Dojan. Let's just mark all of this, and perhaps add a note here. Packaging tools, packaging issues. Authors argue that for a tool B that reuses tool A, it is not possible to merely reference a package that contains both the source code of A and the models of A. Instead, they ended up copying and pasting A into B. it is not clear why the packaging of model plus source does not work. The problem is most notable in cases where code A has been modified after it's been generated from model A. If the modifications have been expressed in the transformation or in the model, then there will be no need to package A into components. However, the problem is still present since GMF does not support the possibility of packaging models or transformations into components. In summary, you can conclude that the hypothesis 3 is false. The standard way of extending tools is not supported. Okay. Let me just leave this here. It's clearly something that's not very clear to us, but seems very important. The issue regarding poor documentation or the fact that GMF architecture was hard to understand are not specific to transformation-based development approaches. In this section, therefore, we focus on the transformation aspect of the GMF framework. In particular, we will focus on the GMF transformation, since we did not find any problems with the EMF transformation. Table 2, we have given an overview of our main suggested improvements and the problems that they are related to. In the following, we discuss each suggestion in turn. Problem. The dialogue-based GMF transformation did not work and was time-consuming to use. Avoid human interaction during transformation execution. Very good. Unclear whether the changes to presumably it's going to be quite important. Unclear whether changes to generated artifacts will be preserved under subsequent transformation executions. Expose the transformation language to the end user. Avoid changing generated artifacts. Lack of modularity in supports. Incorporate traditional programming language solutions to modularity, clearly. So, avoid human interaction during transformation execution. The GMF transformation from the meta model to the graphical configuration models was wizard-based, i.e. the user could configure the transformation through a series of dialogues. If the transformation was run the second time, the transformation would remember the dialog settings of the previous run of the transformation. Or at least that was the idea. Transformation did not work properly, but if we ignore that, we still think that the use of dialogues is bad. First, clicking through a series of dialogue each time the transformation is run is time-consuming. Even though we had a stable meta model to begin with, we ended up generation the editor countless of times. Since the mechanisms of how the transformation worked was hidden from the user, it wasn't clear how to change in the dialogue option would affect the transformation. Not exactly the best of Englishes, but we will just keep this in mind. Let's make sure that our recording is going as expected. Based on our experience, we therefore think the use of transformation executors that require human interaction is a bad idea. As previously discussed, we eventually ended up using an alternative called Eugenia to the GMF transformation wizard for producing the graphical configuration model. This approach enabled us to annotate the meta model with GMF annotations and then generate the configuration files from the annotated meta model without any human interaction. This approach worked far better than the GMF dialogue-based approach. Presumably this is green. Oh. Avoid human interaction. Generation. Authors argue that the generation process should be as mechanical as possible and should not have any human interactions, particularly using UIs. It's a very good point. Expose the transformation language to the end user. The generated artifacts on all three levels had to be modified. From the GMF transformations that generated the configuration level artifacts, For the GMF transformations that generated the configuration level artifacts in the generated model, it was unclear whether or not the modifications to the artifacts would be preserved upon subsequent executions of the transformations. One of the reasons for this was that the transformations were hidden from the user. Without understanding how transformation works, it's also hard to understand how the transformation generates its output. We therefore suggest that transformation should be made visible to the user in the same manner as source code is often made available to programmers. Furthermore, we believe that for the GMF, okay, this is a very interesting suggestion. Sort of goes back to the white box versus black box approach, and we are much in favor of the white box. It's interesting that even though one of the colors works, the other one doesn't. Furthermore, we believe that for GMF model transformations, i.e. the transformations that do not generate the source code, it is better to modify the transformations that generate the model artifacts as opposed to modifying the generated artifacts, because this gives the user precise control over what the transformation generates. This suggestion is made on the basis of our experience with the language Epsilon Object Language, EOL, which we use to customize the GMF transformations that produce the configuration level models in the generator model. This approach worked very well. EOL removed the need for modifying the generated artifacts and enabled us precisely control the output of the transformation. Furthermore, it was not more difficult or more time consuming to customize the transformation than to modify the generated artifacts. One may think that requiring the end user to learn a new language, the transformation language, could be a problem. However, in our experience with EOL, suggests otherwise. In fact, after only seeing a couple of examples of EOL, we were able to customize the transformation as needed. Contrasting this with the months spent on modifying the generated GMF source code, the effort required to learn how to use the language becomes negligible. Regarding the GMF transformation, breathe and expand, that generated the source code, it was fairly clear what parts of the code the expand transformation would change or leave unchanged when it was executed. This is because expand enables the user to annotate methods in the generated code to indicate whether or not the method should be overwritten when the transformation is executed again. Okay, so this is the answer to our question. Actually, expand allows for annotations in methods of the generated code indicate whether the methods should be overwritten or not. However, we believe that it would have been helpful to increase the granularity and flexibility of this annotation scheme. For instance, okay, let's just make a note here. For instance, it would have been helpful to indicate that certain parts of a method, not just the whole method, that have been modified and should not be overwritten. Okay, parts of a method, that's a bit strange. With regards to source code generators, we do not have enough evidence to determine whether or not the need of modifying generated code as opposed to modifying the transformation is a bad idea. So, 6.3. Incorporate traditional programming language solutions to modularity. The GMF transformation from the generated model to the source code model can be customized and expanded as explained in section 2. However, we do not believe that this manner of customization is a good one. It is essentially the same as copying the source code of a library into the current project and then overwriting the code. It is better to package the library into a component which can be invoked to a public interface or extended to subclassing public classes. We believe that transformation language should have similar extension capabilities. After all, GMF can be seen as a common library where the different certain parts of the code are transformations. This is very important. This is exactly the approach we're taking. Fortunately. It's probably pinky really. Related work. There are not many empirical studies on applying model-driven development in industry settings. Survey literature reporting experience applying MDE in industry settings can be found in 13 Okay, paper which we read already. I guess you could probably highlight it. Very good paper, in fact. There is too little evidence to allow generalization of results. Nevertheless, many of the studies mentioned in the survey reported 25% productivity gain using MDD over conventional development. The paper 13 does not address GMF in particular. Papers that do consider GMF in particular are 1, 6, 10, 14. Both 1 and 14 compare GMF against other domain-specific language tools. According to 1, GMF is the most difficult to use, but it generates very usable editors. The paper 14 compares GMF against Microsoft ESL tools and concludes that GMF seems to be better accepted by participants of their study. In 6, the authors do report the experience of developing a network modeling tool using GMF. They make two main conclusions. A high level of programming experience is needed to use GMF properly, and GMF should be made easier to use by domain experts with no particular programming experience. GMF has shortcomings in providing support for modeling at different abstraction levels. In 10, the authors reports on a case study where software with identical functionality was created twice, one using conventional development without code generation, one using GMF. The study concludes that development using GMF was about 9 times faster than conventional development, and that GMF produced much higher quality code. A threat to the validity of the study was that the conventional development was not based on EMF or GF but on .NET. And according to 10, an immature graphical library. Very interesting. Conclusion. We have presented an evaluation of GMF based on our experience in developing the coras tool. Our hypothesis is that GMF shortens development time and that it results in more reliable and more maintainable systems than an alternative development approach which is not based on code generation. Our evaluation suggests that GMF does shorten development time, but to a smaller degree than we initially expected. Furthermore, we believe that the use of GMF may result in more reliable systems, but that it results in less maintainable systems according to our definition of maintainability. So, interesting conclusions. It's very difficult to make evidence for MDE studies, really. For code generators that produce codes that to a little or no degree should be modified, like parser generators, compilers, or EMF to a certain extent, it is perfectly reasonable to hide the transformation from the developer, letting all the work be done at the model level and in customization files. However, we believe that it's not okay for transformations, e.g. GMF transformation, that must be extensively modified, either by modifying the transformation itself or the generated artifact. In fact, we believe that in this case, the transformation should be pushed to the forefront of the development, that the developer should be expected and accommodated to modify the transformation. Okay. GMF does offer the possibility of modifying one of the 3 GMF transformations, but in GMF tutorials and other documentation, this possibility is treated more like an advanced feature than an important part of the development, on par with e.g. configuration model customization. In fact, the developer was not even aware of the possibility until far into the development process. Finally, we believe that the transformation should be extended in much the same way as libraries are extended when programming. Currently, this is not possible in the transformation of GMF. Right, here we are. What can you say about this paper? It's a very interesting paper, as with most papers we read. One has to be very careful with any study that tries to tell you whether MDE is good or bad for development, or whether MDE is better or worse. Part of the work I've done in my thesis is to describe the difficulties of evaluating if MDE improves or worsens the development process, and I think it's extremely difficult to reach any conclusions that are scientific, I guess. They're all localized conclusions, but they're very difficult to extrapolate. And the authors are quite good in that, because they've made it quite clear in the beginning of the paper, when they were discussing their method and their hypotheses, they've made it quite clear all the challenges that you have in this sort of scenarios. So I think that's a very, very nice, well-written paper, very realistic paper. And I think that generally they just want to give their experience so you can benefit from it. So in that sense, the main use of this paper really is to try to understand the uses of this tool and how it correlates to our tool. So Dogen and GMF are very different in the sense that GMF is designed for you to create your own DSL and to create languages. Dogen is not designed for that. Dogen is designed to be just a way to assist regular developers in code generation. And it tries to be kind of a half black box, half white box sort of code generator. In that, ideally, if you don't want to, you don't have to look into how the transformations are made. But if you do want to, then you can peek under the covers. But we are hoping that for the majority of use cases, at least for non-experienced developers, you don't have to. So some of the advice that they give here, which I think is quite useful in the case that you're building your own DSL, we can't really take it because, for instance, we don't really see that the role of an average developer is to change transformations. I think this is just too complicated. And that's one of the reasons why I think MDE tends to fail when in a normal development house, is because a typical developer doesn't really want to know about meta models and transformations and all these complicated things. So for advanced use cases like the use case of this paper, I think is very, very good point, and all the things that I mentioned here are very good. But our perspective is coming from the other end, where we're trying to introduce people to this way of doing things. So for us, we're trying to avoid exposing too many of the concepts, too much of the machinery. It's a bit like compilers. It's probably useful for you to understand the phases of a compiler, understanding intermediate languages and things like that. It's actually probably make you a much better developer. However, it's not very frequently that you're going to be changing a middle end of a compiler, or the front end, or the back end. And that's kind of how we see these MDE tools. For a typical developer that's not experienced, we're trying to go the other direction. So the paper does give us some interesting facts to build on, but it's not quite on the same wavelength as we needed for our research. So all in all, very interesting paper. Thanks for watching.